So in the past couple of videos, we've been talking about the wave properties of light, and we were talking about, for instance, the interferometry or the interference patterns that you see from light from the double slit experiment. Now let's take another test of the behavior of light. And so in this test, right, we have a photoactive plate, which if we shine light, again, we're thinking about it as a wave, right, at this plate, what we expect from this plate is that when you have an energy of input from the light, you're going to ejection of an electron out, okay? And so we can measure both the number of electrons that are ejected during this experiment and importantly also the velocity. And so we expect that the higher the amount of energy of the input light, the higher the velocity will be, okay, of the ejected electron, all right? And so for waves, right, the intensity of the wave, right, in other words, the intensity of the amplitude, right, is going to be proportional to the energy, okay? So the energy input. And so we expect as we increase, our hypothesis in this is that as the intensity is increased, the velocity of the ejected electron will also increase, right, given the same unit area of exposure onto this metal plate. Okay, so what was instead seen, right, is is not exactly what we'd expect from this hypothesis. And so the observation instead was that intensity at certain wavelengths of light had no effect on increasing the velocity. Instead, the increase of velocity of the ejected electron was dependent on the wavelength of the light. So for instance, if light monochromated at 700 nanometers was shined at the plate, there would be no ejection of electrons, no matter the intensity. By contrast, if the light instead that was shined at the plate was 550 nanometers, then you started to get ejection of electrons, and so the velocity could be measured as, for instance, 2.96 times 10 to the 5th meters per second for an input of light at 550 nanometers. Increasing the intensity in this case had no effect on the velocity of the ejected electron, but it did affect how many electrons were ejected, right? And if we went to, if this is taken to 400 nanometers, I know this is a little hard to see, so I'll write this out here. The velocity of the ejected electron was 6.22 times 10 to the 5th meters per second. So going from 700 nanometers to 500, that shows no ejection of electrons, to 550 nanometers, which does see ejection of electrons, to 400 nanometers, which also sees ejected electrons. We see going from 550 to 400 nanometers an increase in velocity. So again in this situation, increasing the intensity did not change the velocity of the ejected electrons, just increased the number of electrons that were ejected, okay? And so what we see here is that ejection of electron is dependent on the wavelength, okay? And so remember, the smaller the wavelength we go to, the higher in energy we go, based on the equations we talked about in an earlier video. And so what the dependence was actually on was kinetic energy, right? So the velocity is going to be dependent on the kinetic energy, and that kinetic energy of the ejected electron was equal to h nu, which is Planck's constant, and then the frequency, right, of the light minus a work function. And this is a threshold function, or a threshold energy that is required, or a minimum amount of energy, right, that is required in order to eject electron in the first place, okay? And so what this equation basically says is that this has to be, right, the energy of the input electron, or the input light, excuse me, has to be greater than this work function in order to get any kinetic energy. And as you increase, right, the energy, right, if we remember that energy equals h nu, as you increase the energy, that's going to increase the kinetic energy past this work function, and there you observe a higher velocity of the ejected electron. And so what this tells us, all right, is that this is behaving more like a particle. So for example, what this is kind of like is if we roll a ball, or throw a ball, for instance, at a piece of wood that is maybe lightly glued down to the surface of a table, okay? So if we throw the ball too softly, right, it won't have any effect on the wood. The wood will just stay there, the ball will bounce off, nothing will happen, okay? But if we throw this fast enough, then we're going to push the wood, right, knock it down, okay? And if we throw this ball even faster, right, then this wood may start going a further distance from where it was glued down to. So this is, we can think of this, right, if we think of the ball, the incoming ball as kind of the light, and this as the work function, right, how much energy is required to move this board as the work function in this experiment, then we kind of get this picture that, wait, light is actually behaving as a particle, right, instead of a wave in this case. And that's exactly what's happening. It's the best way to describe what's happening in this experiment. And so this brings up the idea of wave-particle duality, where depending on the experiment, right, light might exhibit properties of a wave, such as interference, or properties of a particle, such as the photoelectric effect. And so the name for a quote-unquote a particle of light is given a photon. Right? And so we call these are kind of what we use as our discrete units of a light particle.